Okay. So we have started week 11 in the previous session itself, and today we will continue with week 11. Okay, fine. So what are the things we have seen so far in week 11? So we saw what are higher order partial derivatives, right? So in higher order partial derivatives, we started with what are second order partial derivatives. So second, given a function of two variables, f of x comma y, the second order partial derivatives are the partial derivatives of the partial derivatives. So we know that they are fxx, fyy, fxx, fxy, and fyx. So these are the second order partial derivatives. And what is that we should know about the second order partial derivatives? Mainly these two, which are called the mixed partial derivatives. Okay. So what is it we should know about them? So in most of the cases, they tend to be equal. When they are not equal, from this theorem we know. Let f of x comma y be a function defined on a domain D in R2 containing a point A and an open ball around it. If the second order mixed partial derivatives fxy and fyx are continuous in an open ball around A tilde, then fxy at A tilde is equal to fyx at A tilde. Okay. So what is the condition you need to check that they are equal? The mixed partial derivatives fxy and fyx, they should be continuous in an open ball around A. If this happens, then you know that this condition is satisfied. Okay. So this is Clauret's theorem for functions of two variables. Okay, fine. So here is an example we saw. So for this example, we saw that fxy, the mixed partial derivative at the point 0 comma 0 is not equal to fyx at the point 0 comma 0. Okay, fine. Now second order partial derivatives for functions of n variables. So if you have more than two variables also, a similar second order partial derivative can be defined, right? So we have seen some examples for this as well. And then we saw what are higher order partial derivatives. What are higher order partial derivatives? Just like we have taken second order partial derivative, we can take third order, fourth order. So like this, we can keep on finding the derivative, right? So an appropriately modified statement of Clauret's theorem holds. So you have to assume the continuity of the partial derivatives at the specific point for the mixed partial derivatives to be equal. Okay. So for example, for the third order derivative, maybe fyz is equal to at some point A tilde is equal to fyx, let's say, for example. Okay, if these two functions are continuous at this point A tilde. So this is the modified Clauret's theorem for function of three variable for this mixed partial. Actually, there are more than one mixed partial, two mixed partial derivatives in the case of three, right? So you have to write the statements accordingly for each case. Okay. So that is why in general it is mentioned an appropriately modified statement of Clauret's theorem holds. Okay, fine. The next concept is the Hessian matrix. Yes?
Excuse me, ma'am. Can
Yeah.
you roll up a bit?
Sorry?
Ma'am, can you please move to the previous slide? The
Yeah, yeah.
ma'am, in that zero when xy is equal to 0, 0, ma'am, that part I could not understand. The
This
previous,
one?
ma'am, before this, ma'am,
This
yeah,
one?
this one, this example advising caution, ma'am, this part, ma'am.
See, what does it say here in the previous theorem, Clauret's theorem, that the mixed partial derivatives are equal only when the mixed partial derivatives are continuous in an open ball around A tilde. For this function, the mixed partial derivative fxy and fyx at 0, 0, they are not continuous. So for this function, fxy and fyx
Next.
at the point 0 comma 0 are not continuous.
Okay.
And because of this, you see that this happens, that they are not equal.
Okay.
Ma'am,
Yeah.
the function need not be continuous in all real number, not just at a tilde.
Yeah, because we are talking about the equality only at a tilde. Yeah.
Okay.
Okay. Fine. So the next concept is what is a Hessian matrix and why we need it. So the analog for this for the one variable function comes from the second derivative test. So the second derivative test helps us to classify the critical points as local maximum, local minimum, saddle point. So to classify the critical points for functions of several variables, we need the concept of Hessian matrix. There was a student who asked, is there any logic behind this? Are you there?
Yes, ma'am.
Actually, I could not find a proper document for this, but I have found a link where description is given. So mainly they are using the concept of, there is this concept of positive definiteness. So in linear algebra, when you study advanced linear algebra, so there is this concept of positive definite matrix, non-negative definite matrix. So such concept is there when you go to higher linear algebra. So for symmetric matrix only, this concept is used, and using that concept only this theory is developed. So I will give you the link at the end of the session. Okay.
Okay, ma'am. Ma'am, I will be able to understand that.
Can you please be a bit louder?
I will be able to understand that thing.
Yeah, you
That
just
linear
go through,
algebra type.
yeah, you can go through it and see. Okay. Fine.
Okay, ma'am.
Excuse me, ma'am.
Yeah.
Ma'am, you just now said that while explaining the Hessian matrix about this word called saddle point. Ma'am, what is that saddle point?
I hope you have attended the previous sessions. So what is a saddle point? I have given several examples for what is a saddle point, how to describe it, everything I have told you. For example, in the case of function of one variable, so you see that this is the function we usually take, like x cube or any odd power you take, x power 3 or x power 5 or something. So what happens at x is equal to 0? What is the derivative of the function at 0? What is the derivative? First of all, f of x is equal to x cube. What is the derivative?
3x square.
3x square. So f dash of 0 is
0.
0. So f dash of 0 is 0 means you see that you at this point you have a critical point. At x is equal to 0 is a critical point. Okay, x is equal to 0 is a critical point. But f has neither a maximum nor minimum at 0. F has neither a maximum nor a minimum at 0, right? At 0 you see that on left side the values are lesser and the right side the values are higher. So you cannot say that it is either a minimum or maximum, local minimum or local maximum, right? So that is why this point is a saddle point in the case of one variable functions. For functions of several variables, we have given few other figures which you can refer to the lecture for week 10. I have given some examples also. Here also we will see some functions for which what is a saddle point we will find. Okay. So this is what is called as a saddle point, and I have also given an explanation why the name saddle point and everything. Please go to the lecture and see it. Okay.
Okay, ma'am.
Fine. Okay. So now what is this Hessian matrix? So Hessian matrix consists of all the partial derivatives, second order partial derivatives. Okay. So for example, what is the Hessian matrix in the case of functions of two variables? In the case of functions of two variables, Hessian matrix is nothing but fxx, fxy, fxy. We are assuming that these functions are continuous for Hessian test. So I am straight away writing the symmetric matrix here. Okay. So this is your Hessian matrix. Okay. Now how are we going to use this
Excuse
Hessian
me,
matrix? Yeah.
second row second first term is yx partially.
Yeah, that is what I told you. Yeah, this is actually yx and this is xy, or how is that so? So this is fx2 x1, right? So it means this is actually yx, this is xy. That is what I told. For Hessian test, we are assuming the continuity of the partial derivatives. That is why I straight away I wrote fxy, fxy in both the places. They are going to be equal for what we are going to consider. But anyway, yeah, this is the original form of the Hessian matrix. Okay. Now let f of x comma y be a function defined on a domain D in R2 and A be a critical point of f such that the first and second order partial derivatives are continuous in an open ball around A tilde. Okay. So in that case, you know that this means what you know? You know that fyx at A tilde is going to be equal to fxy A tilde. So what happens? This means your Hessian matrix HF is a symmetric matrix. So what is a symmetric matrix? You all remember, right? The transpose will be equal to the matrix. Okay, so it means what? These two elements are same. Okay, so in that case, how are we going to apply the Hessian test? If the determinant is positive, so first case is, this is the case 1. So in case 1, you have a positive determinant. So when you have positive determinant, depending on the sign of the second partial derivative at A tilde, you can decide whether A tilde is a local minimum or local maximum. And if the sign is negative, then you conclude that A tilde is a saddle point. So this is case 2. And the test is inconclusive if the determinant is 0. Inconclusive in the sense that from this test, we cannot conclude whether you are having a local maximum or local minimum or a saddle point at this point A tilde. Okay. So this is the Hessian test for functions of two variables, and we have seen quite some problems for applying this test. Here I have
No, ma'am.
Yeah.
When Hessian matrix is equals to 0, then how we will use another method to find what it is, maximum, minimum, or saddle point?
Yeah, when Hessian matrix is equal to 0, the test is inconclusive. In that case, either you look at the graph or you look at the values of the functions, or you have to use some other technique to understand what is going on there. Okay, so that case you will not be able to use Hessian test because the test is inconclusive for that matrix. Okay.
Okay, ma'am. We will be learning that method.
No, in this course we are not including that. Okay. Only
Okay,
if
ma'am.
we are restricting, you can use Hessian test and say the test is inconclusive at this point. We will not be asking more than that. But if it is a very simple problem from which you can tell, maybe it is included. I have included one such problem. I will explain how to do that. For a very simple case, maybe we can ask. So that I have explained it, that I have included for explaining. Okay.
Okay, ma'am. Thank you.
Fine. Okay. So now look at this problem. What is this saying? If m denotes the maximum value of the function f of a comma b, which is equal to integral a to b 3 minus 2x minus x squared dx. So this is a simple integration. So now it is given as f of a comma b, right? So when you integrate and substitute b and a, this becomes a function of two variables a and b. So now if you are integrating over possible values of a and b, what is the value of 3m? Here m denotes the maximum value of this function f of a comma b. Okay. So now how to do this problem? First of all, we have to do this integration. So let us do the integration and get what is the function f of a comma b. So let us do the integration. Integral a to b 3 dx minus integral a to b. I'm just splitting the integration 2x dx. If it's not required, you can do it straightforward. So what is it? 3 times of b minus a minus 2 x squared by 2. So this 2 will get cancelled. A to b minus x cubed by 3 a to b. So here we are striking out these 2's. So what is that you are getting? 3b minus 3a minus b square plus a square minus b cube by 3 minus a cube by 3. Okay. So are the signs fine everywhere? So this is the function f of a comma b. Okay. So now you are having a function of two variables. So maybe let us write the variables separately. So maybe the first we write the variable in just for easier calculation. Minus b cube by 3 minus b square plus 3b. Okay. So this is your f of a comma b. Okay. Now for this function, what is the maximum we have to find? So first we have to find the critical points for that. So how do you find the critical points? So you have to find what is del f. So the gradient function you have to find, which is the partial derivative with respect to a and then the partial derivative with respect to b. So what is the partial derivative with respect to a here?
A square, 2a minus 3
3a squared by 3, which is a squared plus
plus 2a
2a
minus 3.
minus 3. And then here minus 3b b squared by
Minus
3.
b
So 3
square
and 3 gets cancelled. So minus b squared minus
plus 2.
2b plus 3. Okay, so this is your gradient function. So now to find the critical point, you have to equate it to 0. So if you are equating it to 0, what is that you are getting? A squared plus 2a minus 3 is equal to 0 and b squared minus 2b. Okay, let's just change the sign for calculation purpose. B squared plus 2b minus 3 is equal to 0. Now this is a quadratic equation. So how do you solve quadratic equation? Can you quickly solve and tell the solutions for these two quadratic equations? What are all the
A minus
possible
3 into a.
Minus 3 and 1.
A minus, yeah,
A plus 3. A is equals to minus 3 and 1.
yeah. So a plus 3 and a minus 1 is 0, and here b plus 3 and b minus 1 is 0. So you get a is equal to 1 or minus 3 and b is equal to 1 or minus 3. Okay. So what are the critical points then?
We get 4 critical points.
You get four critical points, which are 1 comma 1, 1 comma minus 3, minus 3 comma 1, and minus 3 comma minus 3. So these are the critical points. Okay. Now what is the next step to find the maximum or minimum? We have to find, first of all, write what is the Hessian matrix. So for writing the Hessian matrix, you should know what is FAA, FAB, and FBB. So first let us write them. What is FAA? 2A
plus 2.
plus 2. FBB minus 2B minus 2. And FAB or FBA both are 0. Okay, so your Hessian matrix is 2A plus 2, 0, 0, minus 2B minus 2. So this is your Hessian matrix. Okay. Now let us apply the values. What is HF of 1 comma 1? The matrix will become
4 comma minus
4, 0,
4, 0,
0,
0, minus 4.
0 minus 1.
And what is HF of 1 comma minus 3?
4,
4,
0,
0.
0.
You see this is 4, 0, 0, and here minus 6 minus 2 is 4.
4 plus 1.
And HF of minus 3 comma 1 is minus 4, 0, 0, 4. Sorry, 0, minus 4 only. And HF of minus 3 comma minus 3 is minus 4, 0, 0, minus 4. Correct? 0, 4.
Plus 4.
Yeah, plus 4. So now let's check the determinant for each case. So what is the determinant of HF of 1, 1? Minus 16, which is negative. And HF at 1, minus 3, this determinant is 16. This is positive. HF minus 3, 1, this determinant is 16, again positive. And this determinant HF
Minus
minus
16.
3 minus 3 is minus 16, which is again negative. Now what is your test? So if the value is positive, and then you have to look at the second order partial derivative at A till, then you can decide whether it is local minimum or maximum. Less than 0 means saddle point. So here you see 2 points are saddle points. So you see this point is a saddle point, 1, 1 is a saddle point, and the other saddle point is minus 3, minus 3 is also a saddle point. So we have to look at the other two values. So let us look at the other two, second order partial derivative at the other two values. What is FAA at 1, minus 3? This is your FAA.
4.
So you get 4, which is positive. So it means 1, minus 3 is a,
Local minimum.
yeah, 1, minus 3 is a local minimum. Okay. And what about this point FAA at minus 3, 1?
Minus 4.
Minus 4, right? Which is less than
Okay.
0. So this implies that your point minus 3, 1 is a local maximum. Okay, so this is your maximum point. Now let us look at the question again. So if m denotes the maximum value of the function, then what is the value of 3m? That is what is asked. Now you know at which point the maximum occurs. So let us find what is f of. So now your m is equal to f of minus 3, 1. So let us evaluate this. What is your function f a cube plus a squared minus 3a? So a cube by 3. So 27 by 3. And then plus a squared minus 3a plus a square minus
And that
3a.
will be minus 27. No?
Sorry?
Minus 27. No?
Minus 27, a cube, right? Okay, fine. And then you have minus b cube by 3. So minus 1 by 3. And then minus b squared plus 3b. So minus b squared means minus 1 minus 3b. So minus 3. So now simplify and tell me what is the answer you are getting. Do the simplification quickly and tell me the answer. So here this is a plus, I guess. Plus,
Minus 22 with.
here this is a plus. There was a mistake. Did you check that? Please check the answer again.
Minus 4 by 3.
I am getting 32 by 3. So what's going on?
Minus 27 by 3 cancel 9. Minus 3 cancel plus 3.
Okay. So let us see. So minus 9 plus 9, they get cancelled. Minus 3 and plus 3 gets cancelled. So, okay, only this part is there. Maybe what
Minus
is
4
the...
by 3.
So, is there any other error? No, right? B squared minus... Here I made a mistake again. Minus 3a, right? What is minus 3a? What is minus 3a? This
Plus minus.
value? minus 3a means this value becomes plus 9. Now check the answer again. So now you will have, so 9 minus 1, 8, 8 plus 3, 11, 11 minus 1 by 3, so 32 by 3. Is it fine now?
Yes, ma'am.
Okay. So now this is your maximum value. So m is 32 by 3. So what is the question? They are asking what is the value of 3m. So 3m is equal to 32. Okay, fine.
Yes, ma'am.
Okay. Okay. So let's move to the next problem. Let f of x comma y. So this is just based on the definition of how the critical test works. So let f of x comma y be defined in a neighborhood of a comma b, and d of x comma y is equal to fxx fyy minus fxy square. So this, what is this? This is nothing but the determinant of Hessian matrix, right? So this is nothing but the determinant of Hessian matrix. Suppose a comma b is a critical point of f. Which of the following options are true? So if the determinant is positive and the second derivative is also positive, then a comma b is a point of local minimum. Is it correct?
Yes, ma'am.
Yeah, it's fine. What about this? If d of a comma b is less than 0, then a comma b is a point of local maximum.
No, ma'am. Saddle point.
So if it is less than 0, it should be a saddle point. So this is incorrect. And what about option 3? If the determinant is 0, if this value is 0, then a comma b, we don't know. The test is inconclusive. So it may be a minimum, maximum, or it can be also a saddle point. So is this correct?
No, ma'am.
No.
Because we cannot say, na, here saddle point must be
Yes,
included.
ma'am. It is right.
That is what is saying. We cannot say. So it may be a minimum or maybe a
true.
maximum, or it cannot be neither of maximum or minimum. That is, it is a saddle point. It can be anything. We don't know. That is what is mentioned here, right?
Yes, ma'am. Yes.
Yeah. Okay. And if d of a comma b is less than 0, then a comma b is a saddle point, right? Okay. Fine. So someone asked how to identify without the Hessian test. Yeah, here is the thing here. Okay. Now, look at this question carefully. This is a very simple question to understand that concept here. Choose the correct statement about f of x comma y is equal to x power 4 plus y power 4, where you are given the determinant of Hessian matrix here. 0, 0 is the only critical point. So what is the gradient function in this case?
4x cube,
4x cube, comma
4y cube.
4y cube. Okay. So now, what are the critical points then?
0, 0.
Yeah, x equal to 0 and y is equal to 0. So 0, 0 is the only critical point. That is true. And what about the determinant at 0, 0? So let us look at the determinant at 0, 0. Obviously, what is fxx? 12x square. And what is fyy? 12y square. And what is fxy? 0. So now what is your d of x comma y? D of x comma y is 12 into 12, 144 x square y square. Right? Now what is d of 0, 0?
0.
0. So if d of 0, 0 is 0, what do you know from Hessian test?
It is we cannot say anything.
Hessian test is inconclusive. We cannot conclude anything from Hessian test. Okay. So this point at least is correct. D of 0, 0 is equal to 0. This is correct. So now we are given two options. So one is saying that this is a local maximum, and the other one is saying that it is a local minimum. Okay, let us see. But anyway, this option is incorrect because it is given that the d of 0, 0 is positive. So this is incorrect. The only thing we have to check is whether this is correct or not. Okay, so please listen carefully. A very simple thing, only. So here, in general, you take any f of x comma y. The function is defined as x power 4 plus y power 4. You take for any x comma y not equal to 0 comma 0. They take any value other than the origin. Then what can you say about f of x comma y and f of 0 comma 0? F of 0 comma 0 is 0, right? So what can you say about the value of f of x comma y for any non-zero x comma y?
Positive. It will
It is
remain
positive.
positive.
So it means it is always greater than 0, right? So it means what can you say from this?
It's an increasing function.
Yeah? Which one is the, so you see at f of 0 comma 0 is the lowest value for this function. So it means what can you conclude from here? At 0 comma 0,
is minimum.
f takes the minimum value. So in fact here 0 comma 0 is a local minimum. In fact, absolute minimum in this case, correct? Because throughout the domain, if you take any other point other than 0, you see this is the minimum value. So do you understand? Just by a simple logic, you are identifying whether it is a minimum or not. Okay, so in many cases, it is not this simple, but you see for some certain examples, this is very simple. You can identify from the logic of the given function. Is it clear? How are we saying that this is a minimum, the function takes a minimum at 0, 0? Is it clear for everyone? Okay.
Yes, ma'am.
Okay, fine. Okay, so the next question, okay, this option is so correct. So what is this question? A very simple one only. Suppose that is equal to f of x plus y times of g of x for some polynomial function f and g. Which of the following option is true? What is zyy? First, what is zy? What is zy for this function?
Gx.
G of x. And what is zyy?
0.
0. Right? So very simple. Okay. So we have seen quite some examples for understanding Hessian test for functions of 2 variables. Now let us move on to Hessian test for functions of 3 variables. Okay, fine. So now let f of x comma y comma z be a function defined on a domain D in R3. Let A tilde be a critical point of f such that the first and second order partial derivatives are continuous in an open ball around A tilde. Then the Hessian test can be applied to check the nature of the critical point A tilde. Okay, fine. So how are we doing that? If you are seeing that a second derivative at A tilde, and then you are, okay, first what is the Hessian matrix? Let me write. So the Hessian matrix is, since we are assuming continuity of the second order partial derivative, straight away I am writing the matrix as a symmetric matrix. Okay, so now I'm going to split it in this way. So this is part 1, this is part 2, and this is part 3. Okay. So first thing, what is the step 1 you are going to do? step 1, just I'm giving a name, and let us say alpha is equal to determinant of your Hessian matrix at the point 8. So calculate this, find this. Okay, so if your alpha is 0, straight away you can write test is inconclusive. Okay, and if your alpha is not equal to 0, then go to step 2. Then you do step 2. In step 2, let us call this value to be beta. So beta is now the determinant of this 2 by 2 matrix here. So fxx fyy minus fxy square at 8 tilde. So find this. Okay. So now if beta is positive, or I will write the other thing. If beta is either less than 0 or less than or equal to 0, then what can you say? If beta is less than or equal to 0, you can say that A tilde is a saddle point. Okay, before that, this condition also we need to include. So first of all, your alpha should be positive and your beta is alpha is positive or negative. Okay, alpha is either positive or negative and your beta is less than or equal to 0. In that case, you can write A tilde is saddle point. Okay, and if alpha is positive and your beta is also positive, okay, and if your alpha is less than 0 and your beta is positive, then go to step 3. Step 3, you find fxx at 8 tilde. What is fxx at 8 tilde? So depending on this value, now maybe I call it as gamma. Okay, now you find fxx at 8 tilde. Now if your gamma is also positive or negative, then you can decide whether it is a local maximum. Okay, so here alpha is positive, beta is positive, and gamma is here in this case positive. Then it is local minimum. Local minimum. And if alpha is positive, sorry, negative, beta is positive, and gamma is negative, in this case it is a local maximum. Okay, so these are the steps for Hessian test for classifying critical points for function of 3 variables. So what is it you need to do? First, write the Hessian matrix, find the determinant of the matrix. If it is 0, you stop it with step 1 itself. So test is inconclusive. When if alpha is non-zero, then you find beta. And if beta is less than or equal to 0, you write A tilde as a saddle point. But if beta is positive, then you go to step 3. Step 3, you find gamma. And in gamma, you find whether it is gamma is positive or negative. Depending on whether alpha is positive and gamma is positive, local minimum. And if alpha is less than 0, gamma is less than 0, it is local maximum. Okay. So all other cases you see here, all other cases in step 3 lead to saddle point. What does this mean? What does this mean? Suppose your alpha is positive but gamma is negative. Then what happens? Suppose alpha is positive and gamma is negative. Then what happens?
Saddle point.
Yes, saddle point. Same way, if alpha is negative and gamma is positive, again it is a saddle point. So only this particular combination if you get, then you will get a local maximum or minimum. and all other combinations you will get only saddle point whenever the determinant is non-zero. Okay, whenever the determinant is non-zero, only these two conditions are going to give you local minimum or maximum. Any other combination of alpha, beta, gamma is going to give you only saddle point. Okay, fine. So what is that you need to remember? Only this much. So if you remember this, all other points when alpha non-zero, they are saddle points, and alpha 0 test is inconclusive. Okay, it may look lengthy, but this is what you actually have to remember. Is this fine? Let us look at examples. So consider this function f of x comma y comma z is equal to x squared plus y squared plus z squared. Now for this function, you have to, for all these examples here, find and classify the critical points. Okay, so how do you find critical points as usual? What is your gradient here?
2x, 2y, 2z.
Yeah. Two x, comma 2y, comma 2z. Okay, so del f is equal to 0 will imply x is equal to 0, y is equal to 0, and z is equal to 0. So what is your critical point?
0, 0, 0.
Yeah. So this is your critical point. Now, what is your Hessian matrix? Let us write the Hessian matrix. What is fxx?
2.
Fxy? 0. Fxz is also 0. And fxz here 0. This is 0, 0, 0, 0, 2. Is this fine? The matrix? Okay. So now
Yes.
you remember you have to consider three things. Okay. So now what is your alpha? That is the determinant of HF at 0, 0, 0,
8.
8, which is positive. So we can go to step 2. It is non-zero, so we can go to step 2. Now what is your beta? Beta
4.
is so 4. Now this is again positive. So we can go to step 3. And your gamma is 2.
2.
So you see alpha is positive, gamma is positive, and beta is positive. So which case?
Local minima.
The first one. So you see this implies that 0, 0, 0 is a local minimum. Simple, right? Oh. Now here also another simple case. So this is your gradient function. So what are all the critical points here again? 0, 0, 0. So this is the only critical point for this function. Now for this function, what is your Hessian matrix? Minus 2, 0, 0, 0, minus 2, 0, 0, 0, minus 2. Correct? Okay. Now, what is alpha? What is your alpha?
Minus 8.
Minus 8. Okay, so we can go to step 2. What is your beta? Beta is
4.
4. So we can go to step 3. And what is gamma?
Minus 2.
Minus 2. So which is less than 0. So this case is
Maxima. Local maxima.
local maximum. So you see that this point 0, 0, 0 is a local maximum.
And can we directly conclude here, because in the first example we did x square plus y square plus z square, and here it is just negative, so minima will become maxima.
Yeah, you can say in that way as well. Yes. Okay. So f of x comma y comma z is equal to, now it is given as this function. Now what are the critical points? They are going to be again the same. The critical point, what is the only critical point? Zero comma 0 comma 0 is your critical point. And what is your Hessian matrix? 2, 0, 0, 0, minus 2, 0, 0, 0, 2. Now for this matrix, what is the value of alpha? Determinant of HF of 0 comma 0 comma 0?
That's it.
Minus 8. So we can go to step 2. So then you find what is beta. What is your beta?
-4.
Minus 4. So if beta is minus 4, do we need to go to step 3?
No, ma'am.
So straight away from here, you can say that 0 comma 0 comma 0 is a,
Saddle point.
yes, it is a saddle point. Okay, fine. So here we have another example. So here also the critical points are nothing but 0 comma 0 comma 0 only. Okay. Now for this, what is the Hessian matrix?
4, 0, 0.
4, 0, 0, 0, 4, 0, 0, 0.
4.
No. I made a mistake, right?
Well,
Second derivative is 12 x square, 12 y square, 12 z square. So now HF of 0, 0, 0 is a zero matrix, null matrix. Okay, if it is a null matrix, you know that alpha value is 0. So we don't have to go to step 3. So what can you say from here? 0 comma 0 comma 0. The test is inconclusive at 0 comma 0 comma 0. Right? But what is that we know from the function values? I told you the
will be a
technique
minimum.
of simple functions we can tell, right?
Yes, ma'am.
By observation, what can you tell?
Will be a minimum. Critical point here.
F of x comma y comma z is greater than 0. That is f of x comma 0 comma 0 comma 0 for all x comma y comma z not equal to 0 comma 0 comma 0. So what is that you can tell from this? The local, also global minimum, correct? Yes? Right? Okay. So the next question here is f of x comma y comma z is xy plus yz plus zx. Now what is your del f again? Y plus z, x plus z, and z plus z. X plus y. Right? Now, if you are equating del f to 0, you get three equations. Y plus z is 0, x plus z is 0, and x plus y is 0. So from this you get x is equal to minus y is equal to minus z, correct? So this is what you are getting. So x is equal to minus y is equal to minus z. X is equal to minus y, x is equal to minus z, but also you get y is equal to minus z, right?
Yes, ma'am.
So we have to be careful while writing this. So Let's do it step by step. Suppose you are clubbing this 2, then you get z is equal to minus x is equal to minus 1. This is what you get from this 2, right? And here you are getting x is equal to minus 1. So now it means what? It means what? If your minus yx is equal to minus x, this means your x is 0. If x is 0, then you know all the other values are 0. So what is the critical point? Only critical point is again 0, 0, 0. This is fine for everyone, right? Yeah? Okay.
Yes, ma'am.
So now what is the Hessian matrix? So fxx is 0, fxy is 1, fxz is 1. Same way here 1, 0, 1, 0, 0, 1. Sorry, 0, 0, 1, 1, 0. 1, 1, 0. Right? This is your Hessian matrix. Now what is value of alpha? What is the determinant of this matrix? First is 0 minus 1 times of 1 minus not 1, 0 minus 1, and then plus 1 times of 1 minus 0. So this is 1 plus 1, 2. Correct? Which is positive. So we can proceed to the step 2. What is your beta?
Minus 1.
Minus 1. So should we go to step 2 then?
No, we should not go to step 3.
Straight away we can say that 0,
Saddle
comma 0, comma 0 is a saddle point. Okay? Fine. Okay. So the next question here. So now what are the critical points for this function? First, what is the gradient vector for this function? 4x cube plus yz. 4y cube plus xz. 4z cube plus xy. So this is your gradient function. Now 4x cube plus yz is equal to 0. 4y cube plus xz equal to 0. 4z cube plus xy is equal to 0. Okay. So what is one obvious critical point?
0, 0, 0.
Yeah, you see that 0, 0, 0 is a critical point. But there must be some other critical points as well. So how to identify that? So I'm going to call this as 1, 2, and 3. So what is 1 times of x? 2 times of y. 3 times of z. From here, what do we get? 4x power 4 equal to 4y power 4 equal to 4z power 4. Which is actually minus xy. This is what we get from all these equations. Now, that is x power 4 equal to y power 4 equal to z power 4. So, what does this mean? X is equal to
1 or minus 1.
plus or not 1 or minus 1. X equal to plus or minus y, and z is equal and x is equal to plus or minus z. Correct?
Yes, ma'am.
So this is what we have. Now it can take many values here. Okay. So now let us see what is happening. So one thing here, whether y and z can have same sign or not, or they can have different signs. So let us see what happens specifically. So now 4x cube, I'm taking equation 1. plus yz is equal to 0. Now what I'm having y and z, suppose they are having, let us assume y and z are of same sign. Case 1, yz is positive. That means y and z are of the same sign. Okay. So in that case, what happens?
X will be negative.
Yeah. 4x cube plus x squared is equal to 0. So it means here x squared, if I am taking commonly, what is that you get? 4x plus 1 is equal to 0, which gives you x is 0 or x is equal to minus 1 by 4. Correct? Okay?
Excuse me, ma'am.
Yeah.
Ma'am, after that yz greater than 0, ma'am, what have you written there in bracket?
Yz?
Greater than 0, ma'am, after that.
Maybe I should write y and z are of same sign. Okay? So it means I am assuming that, so either you are assuming this case x is equal to y is equal to z, or x is equal to minus y is equal to minus z. So this is the first case we are considering. Okay? Maybe I write it this way. This is clearer. Okay? There are two more cases remaining where the signs can be opposite. So you can have x is equal to minus y is equal to z, or x is equal to y is equal to minus z. So this is the other case. So what happens in this case? In this case, so let us look at maybe 4y cube equation 2. 4y cube plus y, it is minus. Okay, so now your y and z are replaced by, sorry, x and z are replaced by minus y or y, right? So it should be either plus or minus y square or minus x square. Wait, here x z is here, instead of x z, both I have minus y into minus y, so plus y squared only, correct? But why we have to take equation 2? What happens in equation 1? Wait, let me check with equation 1 and then we will move to equation 2 if required. So 4x cube, y and z, they are having opposite signs. So one is x and another is minus x in both the cases. So you get minus x squared equal to 0. So this gives you 4 times of x squared into x minus 1. X squared into 4x minus 1 is equal to 0, which gives you x is equal to 0 or x is equal to 1 by 4. Okay. So now what are the corresponding y values in each case you have to write. Okay. So what are the critical points from this you get? What are all the possible critical points? So first one, the trivial one, we have written. Apart from that, we have other combinations. Let us write them. 0, 0, 0. Then when x is 0, y is at 0, this case is considered. And when x is minus 1 by 4, you have all of them having minus 1 by 4, or these two are having the opposite sign. Okay. So here these cases are covered. What about here? Again, x is equal to 0 case is covered. X is equal to 1 by 4 means 1 by 4 minus 1 by 4, 1 by 4, and 1 by 4, 1 by 4, minus 1 by 4. These are all the possible critical points. Is this clear? How did we obtain the critical points? Is this clear? Okay.
Yes.
Now, from this critical points, we need to identify which are the local minimum, maximum, and all that. So first, we need to write the Hessian matrix. What is your Hessian matrix? So here is your fx, fy, and fz. From here, we'll write fxx is 12x squared, fxy is z, fxz is y, and this is same as z, and this is 12y squared, and this is fy z, right? So x. So here this is symmetric matrix. So this is y, this is x, and this is 12z squared. So this is your Hessian matrix. Now at each point, what happens? We need to see. What happens at 0, 0, 0, 0? We don't have to do calculation. Straight away, can you say what happens at 0, 0, 0? HF becomes the null matrix. So the test is inconclusive at 0, 0, 0. Okay, let us move to the next point. Did I leave further space? Right. Okay. What is HF at minus 1 by 4, comma minus 1 by 4, comma minus 1 by 4? All values are negative. What is your matrix then?
L by 16.
So here 1 by 16 if you have. So 12 by 16
3 by 4.
by 4 minus 1 by 4 minus 1 by 4 minus 1 by 4 3 by 4 minus 1 by 4 and minus 1 by 4 minus 1 by 4 3 by 4. Now what is the determinant of this matrix? So let us take 1 by 4 outside, and what is that is remaining here inside? 3 minus 1 minus 1 minus 1 3 minus 1 minus 1 minus 1 3. What is the determinant of this matrix? Can you calculate quickly and tell me? Remember here one thing you can use for finding the determinant. So this is now K. Determinant of KA is equal to, here this is a 3 by 3 matrix. So K power 3 determinant of A. Here we just need the sign. We don't need the value of determinant. We just need the sign. So here K is a positive number. So this is a positive value. So only the sign of determinant of A is what we need. So what is alpha? What is the determinant of this matrix? Calculate it and tell me quickly.
I guess positive.
It
24.
is positive. So if it is positive, then we need to proceed to step 2. So what is your beta? The determinant of this part. So 9 nines are 9 minus 1 8. So again positive, right? So maybe I just write positive because here 1 by 4 we need to consider. So I'll write the beta is positive. And what about this one? This is also positive. Gamma is also positive. If alpha, beta, gamma all are positive, what can you say about this point?
Minima. Local minima.
Local minimum. Okay. So same way you have to calculate for the other parts also. So I don't have space here. Shall I leave it as a homework, or if we have, I guess we have sufficient time in this session. If we have time, maybe I can do it at the end of the session. Or shall I complete this one? What shall I do? We have sufficient time for this session actually.
Ma'am, will the session over at 10:30?
Sorry.
Will the session end at 10:30?
Okay, fine. So here this is for this also we need to classify this point, this point, this point. These three are left. Okay. So for now I'll write it as a homework, but if we have time, we will do at the end of the session. Okay. So almost we are there at the end of week 11. Consider a function f of x comma y comma z is equal to x cube y plus yz. If A is the Hessian matrix of f of x comma y comma z at 1 comma 1 comma 0, then which of the following options are true? So you need to first of all write what is the Hessian matrix. So your A is equal to, what is your function fx? What is fy? X cube plus z, correct? And fz is y. Fine. These are the first order derivatives. What are the second order derivatives? So straight away maybe we write in the matrix. Your Hessian matrix HF is equal to fxx, which is 6xy, fxy 3x squared, fxz is 0. So this is also 3x squared. Fyy is 0. Fyz is 1. Fzx is 0. Zy is 1. Zz is 0. So it is given that A is equal to HF at 1 comma 1 comma 0. So what is this matrix? At 1 comma 1 comma 0. 6, 3, 0, 3, 0, 1, 0, 1, 0. So what is the determinant of this matrix? Calculate quickly and tell me. What is the determinant of this matrix?
Minus 6.
Minus 3.
What is the determinant?
Minus 6.
No one calculated it. Okay, so let me calculate 6.
Minus 6.
Minus 1, yeah, it's minus 6, I guess. Minus 1 plus 3,
Minus 6.
0, 0. Yeah, it's minus 6. And if determinant is non-zero, do you need to calculate the rank? Implies rank of A is
3.
3. You don't have to calculate the rank. Since determinant is non-zero and A is a 3 by 3 matrix, you know that rank of A is 3. So the other options are incorrect. Okay, fine. Consider the function f of x comma y comma z is equal to x cube plus xz squared minus 3x squared plus y squared plus 2z squared. Which of the following options are correct? So at 0 comma 0 comma 0, what happens you need to see. Okay, so first, what is your fx? 3x squared plus z squared minus 6x, and fy is 2y and fz is 2xz plus 4z. Okay. So what is your Hessian matrix then? Fxx is 6x minus 6. Fxy is 0. Fxz is 2z. And here also 0. Here fyy is 2. Fyz is 0. So here also 2z. And 0. And here fzz is 2x plus 4. Now what happens to hf of 0, 0, 0? Minus 6, 0, 0, 0, 2, 0, 0, 0, 4. It is a diagonal matrix. So easier for calculation. Your alpha is, what is alpha?
Minus 48.
Minus 48, so less than 0. What is your beta? Your beta is minus 12.
12.
So it is less than 0. Should we go to step 3?
No.
So this itself tells you that,
Saddle.
yeah, it is a saddle point. Okay, so this is a saddle point. Okay, so I guess we are done with. Okay, one last problem. So again, for this function, what happens at 0, 0, 0 and minus 2, 0, 0, we need to see. So what is fx for this function? So let us rewrite this function. Ex x squared ex y squared ex minus 2z squared ex. So now what is fx? We have to use UV method. 2x e power x plus x squared e power x. Is this correct? Okay.
Yes, sir.
Okay. What is fy?
Ma'am, there will be minus y square and minus z square as well.
Oh yeah, here also we have x terms. Yes, yes. Minus y square e power x and minus 2z square e power x. Yes. And fy is equal to minus 2y e power x. And fz is minus 4z e power x. Okay. Now, what is fxx? Maybe let us write it here. Fxx is 2 times of x e power x plus 2 e power x from the first term. From the second term, again 2x e power x plus x square e power x minus y square e power x minus 2z square e power x. Quite lengthy. So maybe we can simplify this further. 2 e power x plus 4x e power x plus x square e power x minus y square e power x minus 2z square e power x. So e power x taken commonly, 2 plus 4x plus x squared minus y squared minus 2z squared. Okay. Fine. What is now fxy? What is fxy?
Minus 2y e power x.
Minus 2y square minus 2y e power x. Okay, fine. And what is fxz? Minus 4z e power x. Okay. And what about fyy? Minus 2 e power x. And yz
0.
0. Okay, what is fzz? Minus 4 e power x. And what is fzx, fzy? Everything is done. Okay, fine. So we can write the Hessian matrix now. So hf is equal to e power x 2 plus 4x plus x square minus y. I hope I have not made any calculations. I don't have the solution here. Okay. Minus 2y e power x minus 4z e power x. And here also minus 2y e power x minus 2 e power x. Here 0. Here also 0. Minus 4z e power x minus 4 e power x. So now what happens at 0, 0, 0? When you put 0, 0, 0 here, these terms, this term, this term, this term, this term, all this becomes, all of this becomes 0 except the first term. So your HF at 0, 0, 0 is 2, 0, 0, 0, 0, 0, 0, 0, 0. Is that correct? No, no, no. This term is non-zero. It's a diagonal matrix. Minus 2 and minus 4. Correct? It is this matrix
Yes.
at 0, 0. Okay. So now what is alpha? Alpha is 8, 16 positive. Okay. So beta minus 4. So at 0, 0, 0, F has a saddle point. So, and then you have to look at what happens at minus 2, 0, 0. Okay. Let us see what happens at HF of minus 2, 0, 0. What is your matrix? So these terms y and z become 0. Your x is minus 2. So e power minus 2, 2 minus 8. Just calculate it and let us write the simplified answer here. E power minus 2,
Minus
2
Yes,
minus 8 plus 4, right? So minus 2 e power minus 2, correct? And this value here, it is 0. This is 0. This is 0. And this is minus 2 e power minus 2. This is also 0. And this is 0, 0, minus 4 e power minus 2. Okay. Now, what is your alpha here? Alpha is 16 e power minus 2. So, what is the value of e power
Minus 2.
minus 2? What is the sign of alpha? What is the sign
Negative.
of alpha?
Ma'am, alpha is minus 16 e power minus 2. No?
So, e power minus 2 value is?
Ma'am, here in the determinant alpha, it should be 2 into 2 into minus 4, then it is
Oh,
minus
here
16.
I have, instead of multiplying, I have added them. Okay. So, minus 16 e power minus 6. Yeah.
And a negative as well.
It will be
E power,
positive 1 by 6.
yeah. So, what is the answer?
Ma'am, in this case, alpha will be positive.
Yeah, alpha is positive. What about beta? Beta is 4 e power minus 4. So what is e power minus 4? Again, it is positive,
Positive.
right? Okay. What about the gamma?
Negative.
comma is negative.
Yes, ma'am.
So what can you say about this?
Ma'am, here alpha is negative, no?
Yeah, ma'am. Alpha
Alpha
for
is
the
negative.
yeah,
Ma'am,
multiply minus
minus 16.
Oh,
16.
minus 16 is there. Okay, okay, fine, fine. Yeah. So negative, positive, negative. So it means at 2 comma 2, minus 2 comma 0, you must have a local
Maximum.
maximum. Correct?
Yes, ma'am.
Okay. Is it fine? This problem? Okay. So the last topic of almost this course we can say is differentiability for multivariable functions. Okay. So already we
Ma'am,
have seen several
excuse me.
versions of differentiability for multivariable functions. We
Ma'am,
started
excuse me.
with what? Yeah.
Ma'am, I have one doubt. Ma'am, for construction
Sorry,
of
please be
the
louder.
ma'am, for the construction of the Hessian matrix, we take partial derivative of fx, f xx, fxy,
Yeah.
fxz, and the
Yeah.
second row we consider like the yx, yz.
Yx and xy both are same for continuous functions.
If it is not continuous, then we consider the
Mostly
yx.
Hessian test we consider only when the partial derivatives are continuous. Otherwise, the Hessian test does not make sense.
Okay, okay, thank
Okay.
you. Okay,
We
ma'am,
are
thank you.
assuming for Hessian test, we are assuming that the partial derivatives are continuous. Only for such functions only Hessian test is applicable. Okay.
Okay, ma'am, okay, thank you.
Okay. So now, as I told you, we have already seen like for differentiability of multivariable functions, we have seen other versions like what are partial derivatives, what are directional derivatives, and then we saw what are gradient functions. These are some form of differentiability for multivariable functions. But precisely what is differentiability for multivariable functions? And what is we can say what is the analogous concept of differentiability we see in one variable function? In differentiability of one variable function, what is that we see? Let f be a function defined on an open interval around a. Then f is differentiable at a if limit h goes to 0, f of a plus h minus f of a by h exists. So you see, if you are having, this is your function f, okay, and you are having a point a, then what you do? You consider all the points, you start with some a plus h, you start making this h going to 0, that is you are coming towards this, and see where is this function moving to. Okay, so you will get this limit is the slope of this tangent line t. That is what you will get. So initially you will start with the slope of some secant line, and then you will end up with the slope of this tangent line t. That is how you define differentiability in the case of one variable functions. So now, what is the analogous concept for multivariable functions? Okay, so in general, you also define the derivative function in this way, same way. So f dash of x is defined in this way. So its domain consists of all those points for which f of x is differentiable. And you also have this very important fact for differentiable functions, that differentiability at a point implies continuity at that point. Okay, so these are some basic property about differentiability of one variable function. Okay, also if your function is differentiable at a point, then the tangent line of f at a exists, and the best linear approximation of f at a exists. So all these are equivalent conditions. Okay, so analogous concept we will see now in the case of multivariable functions. Now let me just recall few things. What is f dash of a? Limit h goes to 0, f of a plus h minus f of a by h. Now this is the definition of limit of one variable function, right? Now I just want to rewrite it a little bit. So I want to add one more term, or I can say that I will bring this f dash of a to other side. Limit h goes to 0, f of a plus h minus f of a by h minus f dash of a is equal to 0. So the limit is only for this part. Now I want to bring this f dash of a also inside this limit. So what I am going to do is that here what I have done, do you understand? I have just multiplied and divided by h. What is this equal to? What is this equal to? Simply f dash of a only, right? So by making here, I have written limit h goes to 0, h by h f dash of a and included it inside the limit. Is this fine? This step? Okay. Now, this part here, just remember this part here. Okay, and we will look at this definition of differentiability here. And we'll come back. Let f be a scalar valued multivariable function defined on a domain D in Rn, containing an open ball around a point A. Then f is differentiable at A if you have this condition. What is the condition we have seen there? Limit h goes to 0, f of a plus h minus f of a minus h times of f dash of a by h is 0. So this is the differentiability condition, rewritten differentiability condition for one variable function. You see, it is very analogous. So instead of the derivative, you are having the gradient function here. And instead of just h, you are having norm h. Because now h is a vector, it does not make sense to divide by a vector. So we are having norm h here. So you see a very analogous definition is there. Okay. And remember, what is the equation of a tangent plane? The equation of a tangent plane of f at a is z is equal to f of a tilde plus del f of a tilde into x minus e. And this is nothing but also the linear approximation of x at a. Right? So it is also given by f of a tilde plus del f of a into x tilde minus a tilde, the same. So this is the linear approximation. This is x tilde only, right? So this is the linear approximation. Now, do you also remember this formula that there is an equivalent definition for the derivative of a multivariable function, that you can define f dash of a as limit x goes to a f of x minus f of a by x minus a. So using the same trick like you have done here, just multiply this term to this side and multiplying and dividing by h. Using the same trick, if you are rewriting this term, then you see you will get limit x goes to a f of x minus f of, actually this term here, what is that? You will get f of a minus x minus a times of f dash of a by x minus a is equal to 0. Okay, using the same trick you have used there. Now you see this part, what is this part here? What is this part representing? It is the equation of the tangent line. Or the linear approximation of f at a. Okay, so you can write it as limit x goes to a fx minus lf of x by x minus a is 0. So you see that the same kind of relationship we can also obtain in the case of multivariable functions. That f is differentiable at a is same as saying that the tangent plane exists, is same as saying the best linear approximation of f at a exists. Okay. And also the concept that if f is differentiable at a, then it is continuous at a. Okay, so for this course, the concept of this differentiable function, it is enough sufficient if you understand what is the definition, and you should know that these conditions are all equivalent. Okay, that differentiability at a is equivalent to the other two conditions, that the existence of tangent plane of f at a and the best linear approximation of f at a. Okay, so these three conditions are equivalent, and the differentiability at a implies the continuity at a. So if you know this much, that is sufficient for this course. We are not going into problems for differentiability of multivariable functions in this course. Okay, so yeah, we are done with the syllabus here. So today's topic, whatever we have covered, is that clear for everyone?
Yes, ma'am.
Okay, so these are this is what is week 11. So we are completing almost everything in this course. Tomorrow you will have problem session for this multivariable calculus alone. So you can go through all the problems, collect your doubts. Also, you will be solving quite some problems for week 9, 10, and 11. Okay, so make sure you attend tomorrow's session without fail. Yeah, so if you have any other doubts, we can again discuss during the revision sessions. We have 3 revision sessions for NSEM. So week 1 to 4 one session, week 5 to 8 another session, and week 9 to 12 another session. So 3 sessions we are having for NSEM revision also. So you can ask your doubts either in revision session or also you have TA sessions. So make use of all the sessions. If you don't have any other doubts in today's session, we can wind up the session now.
And ma'am, week 12 is week 11 content only uploaded, na?
Yeah, the same only, yeah.
Okay, ma'am.
Okay. So, any other doubts in today's session? Okay, if not, then let's wind up the session. Thank you, everyone.
Thank you, ma'am. Bye. Good.